So I had gotten emailed a few questions on the 5 and 6 review. We'll go ahead and look at those. So this one was divide using long division, number 5. So we have 16y cubed minus 8y squared plus 9 divided by 4y minus 4. You notice that there's not a y term in the numerator. We go right from a number with no y to a y squared. You want every power of y represented, so we would put a 0y in for a placeholder. So off to the side, we'll take the 16y cubed and divide it by 4y. We get 4y squared. And then we take the 4y squared and multiply it times each of these. So we get 16y cubed minus 16y squared. So we multiply the 4y squared times each of these, and then we subtract. And we subtract the 16y cubed minus 16y cubed, that's 0. When we subtract, this becomes plus. So negative 8y squared plus 16y squared, and that would be 8y squared. And then we bring down the 0y. And we repeat the process. So off to the side, I'll take 8y squared divided by 4y. And that would be 2y. So 2y is part of my answer, and I put it on the top here. And then we'll take the 2y and multiply it times 4y minus 4. So we have 8y squared minus 8y. And then we subtract. When we subtract, this will become plus 8y. So we have 8y. Bring down the 9. So off to the side, we take 8y divided by 4y. And that's 2. 8y divided by 4y is 2. So we put plus 2. So 2 is what we're going to multiply over here by. 2 times 4y minus 4. So we get 8y minus 8. And we subtract. So we get 9 plus 8, or 17. And you write your remainder as 17 divided by 4y minus 4 as part of your answer. Does anybody have any questions on any of those steps? Let's see, I also got asked number 14. So our least common denominator is a little complicated here. We have an x plus 5 and an x plus 2 involved. So we're going to use method 2 and build up the fractions. So we'll build up all 4 fractions so that, well, not really. We'll build up these fractions so that we can add them together or subtract them, actually. And for these 2 fractions, the least common denominator is just the x plus 5. But in the bottom 2 fractions, the least common denominator is the x plus 2 times x plus 5. So we'll multiply here by x plus 2 over x plus 2. And over here by x plus 5. over x plus 5. So the least common denominator in the bottom is different than the least common denominator on top here. Well, let's see what we have then. We have the 4 over x plus 5 minus, distribute the numerators, so 5x plus 25 over x plus 5. In the denominator, we have to distribute 7, so 7x plus 14. And in the second fraction, distribute the 8, so 8x plus 40. So now the little fractions can be combined because their denominators match. So here I have 4, and then distribute the minus. So 4 minus 5x minus 25. Over x plus 5. In the denominator, you're subtracting as well, so be careful to distribute the minus sign. So 7x plus 14 minus 8x minus 40. So once the denominators match on fractions, you can go ahead and add or subtract them. Well, let's see, what does that give us then? It would be negative 5x minus 21 and negative x minus, would that be 26? Yeah, 26. Thank you. So once we get down to just one fraction on top and one fraction on the bottom, you can go ahead and flip the bottom fraction over and change to multiplying. So when you're multiplying fractions, you would put parentheses around sums and differences so that whole sum or difference stays together. And the whole sum or difference can cancel, or none of it can cancel. So here the whole x plus 5 can cancel. Does anyone have any questions? Let's go ahead and look at 18 as well. I got emailed that one. So those negative exponents, you were supposed to learn about exponents in Math 094. If you don't remember, a negative exponent tells where to put the factor. So the negative exponent on the x means you can put x to the second power in the denominator. So a negative in an exponent is just a positional thing. It just tells where in the fraction that factor belongs. Unless you don't mind the negative exponent, then you can leave it on top. But we'll put ours in the bottom, and then you can see, well, I have an equation with fractions, so let's multiply by the least common denominator, x squared. And you're multiplying by x squared over 1, so you get x squared over 1 plus 35x squared over x squared equals 12x squared over x. So you multiplied each numerator by x squared, and when you do that, your denominators divide away. So you have x squared plus 35 equals 12x. When you have a quadratic equation, when you have an x squared like that, you should go ahead and get a 0 on one side. So we'll get minus 12x on the left. And then hopefully you can factor the other side. So 0 on one side and factor the other. this does factor as x minus 7 times x minus 5. So the reason we do that, we factor like that, is because now you have two quantities multiplying to equal 0. So these two quantities each stand for a number, and each of those numbers could be 0, because then when you have 0 times something, you get 0. So if x is 7, then the equation is true, or if x is 5, the equation is true. I did get email number 17, but I did post that on Facebook with different numbers.
Can you get email number 4?
Let's just check.
It was on D2L. I answered part of it, but I couldn't get the second one.
Let's take a look. I did put that one on Facebook, but if you want, we could go over it. Oh yeah, we have a few minutes. Okay.
Okay, it's negative 3x. It's f of x equals negative 3x squared plus 7x minus 1. And then it's b, so f of x minus f of a over x minus a.
Okay, great. So f of x means to write the function down with just x's, just the way it is. And then f of a, you put parentheses around because you're subtracting a sum. So you put parentheses around it. And then f of a means put a's in where the x's are. So whatever's in the little parentheses gets plugged in for x. So we have negative 3a squared plus 3a minus 1. So the f of x part just has an x in it. Oh, it should be 7. No, you're right. It's supposed to be 7.
Okay.
I think I was combining the one you have with the one on the internet. Okay. Okay, so you're right. It should be 7a. Okay, good. Then you can distribute the minus and subtract. So we have the negative 3x squared negative 3x squared plus 7x minus 1. And then distribute the minus, so plus 3a squared minus 7a plus 1. So every term will get the opposite sign. So the ones add to 0. You still have the other terms there. And there's a little trick here. Rearrange so that the squared terms are next to each other. So put the squared terms next to each other. Negative 3x squared plus 3a squared plus 7x minus 7a. That way you can factor a negative 3 off of these first two terms. And you can factor a 7 off of the second two terms. So when you do that, when you factor out a negative, then you have positive x squared minus a squared, and that can be factored again. So we want to factor by grouping, but right now these two factors are not the same, so you can't factor them out. But if we keep factoring this x squared minus a squared, then we can keep going. So we get negative 3 times x plus a times x minus a plus 7 times x minus a, and now you can factor off the x minus a. So you factor x minus a off of these three factors, and that leaves negative 3 times x plus a. And in the second term, you factor off x minus a, and that leaves us 7. And now that you're multiplying, so you have this x minus a times this whole thing, now you can divide that away. Up here you couldn't divide because of the plus sign right in the middle there. So x minus a's cancel, and you just have what's in the square brackets. So that's a negative 3x minus 3a plus 7. So that one has a couple little tricks to it, so it's good to look at it. Okay, but if you still have questions, see me after class, and we'll go on with today's work. Actually, I have been emailed a reminder that there is drop-in tutoring with Ruth Hayden. So she's an instructor, really. She's just tutoring this last 7 weeks of the semester. So she's an excellent resource, and if you are having problems with your homework, it's a good idea to sit outside her office and then go in and ask her questions, okay? So that's 9:30 to noon, Tuesdays and Thursdays. Oh, I thought that, I didn't realize it was blowing up something. Let me make it a little wider. Okay.
Thank you.
Yeah. Okay, and then I wanted to address some of your comments that you had. So I had asked, if you were here that day, I'd asked for feedback on how the semester is going for you, and I really appreciated hearing from you. A lot of you had a lot of kind and thoughtful comments that I appreciate. You did have some concerns, though. Some of you said I go too fast sometimes, and I'll try and go slower. Can you help me out with that? Because sometimes I think you're getting it, and you're like thinking she's going too fast, and I'm not knowing that you're thinking I'm going too fast. So when I say if you have any questions, can you just say, can you repeat that, or slow down or something, so that I know, and I'll try and be thoughtful in watching you too to see if you look like you're keeping up. Somebody made a comment about real-world applications, but I wasn't sure if they wanted more or less real-world applications. To be honest, algebra class here anyway is taught as a preparation for other classes. That's why it's a prerequisite for so many other classes. So it's in your science classes that you see a lot of real-world applications, or it's in your statistics class that you'll see real-world applications that this is supposed to be getting you ready for. The idea in our class is that when you see these ugly algebraic things like this, that you're like, oh, I know what to do there, and these will be just small parts of bigger problems that will be in your other classes, and the algebra class that you take with here, Math 101, is supposed to get you all ready for that, so that you're not slowed down, so that whenever you're doing your science class or statistics, you can just keep going and with no problems. Okay, so we don't have a lot of real-world applications in here because that's not the point. I mean, it's nice if we can, and every so often WebAssign puts one in, but it's more to prepare for other classes. And some of you don't like the review. Actually, one person doesn't like the review and the homework, but I've had a lot of people that do like the review and the homework. If it bugs you, if it's like there's too much to remember all at once, then just take your homework assignments and work all the ones from 7.1 today, okay? Because we're doing 7.1, so you can work ahead and do all the ones in 7.1 in WebAssign and do it that way. And then after we do 7.2 Monday, you could do all your future homework assignments, do the ones that say little 7.2s next to them, okay? Excuse me. And so on. And some of you like, well, actually a lot of you said you like doing the homework problems at the beginning of class. Some of you, or one or two of you thought that maybe we spend too much time sometimes at that. I understand that for a lot of you who are getting this and who already have your homework done, this is a review that maybe you don't need. If you want to like work on your phone during that time, or probably better would be to work on like a future homework assignment, that would be fine. I used to do that in class. I would bring my homework and I'd work on it and I'd listen and work and listen. So it's up to you. Multitasking is not the best way to learn something, but certainly when you already have your homework done, that would be a good time to work on the next homework. So thank you for your comments. You don't have to wait till I ask for feedback to let me know how things are going. I'm glad to hear how things are anytime. Let's take a look at 7.1. I have 7.1 and 7.2 on here together. So I took a look at WebAssign to see how they're broke up on WebAssign. And I'll just get that up again so I make sure I don't miss something. So we're talking about radicals. Those are roots. So we're going to talk a lot about radicals in this chapter. The first goal is to just understand what they are. So when we say the square root of 4 is 2, it's because 2 times 2 is 4. So when we say a square root, we're looking for the number you can times by itself and get 4. Now if you put the square root of 2 in your calculator, you get an irrational number that does not end. It's just the decimal expansion just keeps going. So we don't like to round that off. We like to just use the square root of 2 and not round it off to 1.4 or 1.414. Because then if you have the square root of 2 times the square root of 2, that exactly equals 2. Because the square root of 2 stands for the number you can times by itself and get 2. And there you are. You're times the square root of 2 by itself, so you get 2. Whereas if you take off a rounded off version, you don't get exactly 2. So we like to work with the square roots and not the rounded off versions. This would be, the square root of 2 is exact, and this would be an approximation. So we'll be looking for exact answers, not approximations. Same thing with square root of 5. So the square root of 5 stands for the number you can multiply times itself and get 5. So the square root of 5 times the square root of 5 is 5, because that stands for the number you can multiply times itself and get 5, and there it is, multiplying times itself. But the round off version, you get a little round off error if you multiply that times itself. It turns out that if you have negative square root of 5 times negative square root of 5, that also equals 5. Or up here would be better to see. Negative 2 times negative 2 also equals 4, but we don't say the square root of 4 is negative 2. We say the square root of 4 is positive 2. That's called the principal or positive root. Okay, so even though negative 2 times negative 2 is also 4, we ignore that and just take the principal root. Well, we need to see how we're going to simplify radicals. What we want is the smallest number under the radical symbol as possible. This is called the radicand. The number under the root is called the radicand. So is there room? Is that showing? We'll put radicand here. So when I talk about the radicand, I mean the number under the square root symbol. We want that to be as small as possible. So there's different ways to find that. I'm going to show you the prime factorization method. So you would take the 500 and find its prime factorization. So you just start dividing. You'd say, well, that's divisible by 100. That's 100 times 5. And 5 I can't divide anymore. But 100, that's 10 times 10. And each 10 is 2 times 5. So you just keep factoring until you can't factor any more. Each number only has a single prime factorization. So when you get to the ends of your branches, everybody's prime factorization will be the same, even if you started out with 50 times 10 instead of 100 times 5. You'll get the same prime factorization at the end. So what do we have? We have 2 times 2 times 5 times 5 times 5. Well, it turns out that the square root of 500 then is equal to, well, we might as well do that over here, right? We have the square root written out. Okay, the square root of 500 is equal to the square root of 2 times the square root of 2 times the square root of 5 times the square root of 5 times the square root of 5. So that's the product rule for roots. If you have a prime factorization, or any factorization, you can write the product of the roots instead of just all multiply it out together like this. And the reason that's helpful then is because every 2 matching roots multiply to be exactly the radicand. So square root of 2 times the square root of 2, that's exactly 2. square root of 5 times the square root of 5, that's exactly 5, because each little square root of 5 stands for the number you can multiply times itself and get 5. And here I am, I'm multiplying it times itself, so I get 5. So we have 2 times 5, and then there's this extra square root of 5 by itself. So we have 10 square roots of 5. So one way to simplify radicals is to take the prime factorization and then look for pairs. Whenever you have two matching square roots multiplying together, they multiply exactly to equal the radicand. Some of you might have learned to take and think of this as the square root of 100 times the square root of 5, because you had to memorize all the squares and then you take the squares out like that. That's fine if you learned how to do that. You'll still need this method for really big numbers, but this is faster if you did memorize that. I'll be using this method in class, though, because a lot of students don't learn this anymore. Okay, can you find the prime factorization of 72? Can you take the 72 and see how you would divide? You can see it's even, so you can start with 2 if you don't know how else to start. Okay. So you should have got 72 is 2 times 2 times 2 times 3 times 3. So the square root of 72, you can write as square root of 2 times square root of 2 times square root of 2 times square root of 3 times square root of 3. So the two square roots of 2, those multiply to exactly equal 2. And then the two square roots of 3, square root of 3 times the square root of 3 is exactly 3. So we have 2 times the square root of 2 times 3, because we have that extra square root of 2 all by itself. Now multiplication is commutative, that is, you can write it in any order. It commutes, okay, so you can take 2 times 3 times square root of 2. And you probably knew it was commutative, right, because you knew 2 times 3 is the same as 3 times 2. They're both 6, so it doesn't matter what order you multiply. So usually we would multiply the 2 and the 3 together and then say times the square root of 2. So we want the radicand to be as small as possible, and that means that you would simplify by finding the prime factorization, and then you're looking for two matching factors, because those two square roots of 2 multiply to be 2, and the two square roots of 3 multiply to be 3, and so on. Does anybody have any questions? Well, when we have a cubed root, this little 3 here, this 3 is called the index. Okay, so the index is a 3 here. And then we mean the number that when you multiply times itself 3 times yields whatever the radicand is. So for example, the cubed root of 8 is 2, because when you multiply 2 times 2 times 2 3 times, then you get an 8. Well, the cubed root of 2 times the cubed root of 2 times the cubed root of 2 is 2, because there's 3 of them multiplying together. So each cubed root of 2 stands for the number that you can multiply times itself 3 times to get a 2. And here it is multiplying times itself 3 times. So you do, in fact, get a 2. So these are different values. The square root of 2 is about 1.414, and the cubed root of 2 is about 1.260. So you don't want to forget your little indices, okay? If you start out with a cubed root, don't accidentally drop the index. There is an unwritten 2. So when there's no index written, then you have an index of a 2 for square roots. Mathematicians use square roots so often that they just agreed, okay, let's just not write the 2 all the time. Let's just say if there's no index, we're talking about a square root. So, so when you're looking for, like, suppose you have the cubed root of 250, and you want to simplify that, you'd go through the same process as we did with the square root, only this time we're looking for 3 factors that match. So let's do the prime factorization. So it's 10 times 25. Let me make this wider. And then 25 is 5 times 5, and 10 is 2 times 5. That looks like 10 is 25. Let me fix that. So the cubed root of 250 would be the cubed root of 2 times the cubed root of 5 times the cubed root of 5 times the cubed root of 5. So now, because they're cubed roots, I want 3 factors that are equal. And I have that. I have the cubed root of 5 times the cubed root of 5 times the cubed root of 5. So this is 5. So whatever your little index is, that's how many matching roots that you need when you're simplifying your radicals. Okay, you need 3 matching factors to multiply together when you have a cubed root. Whatever your index is, that's what you need. And so you could have a 4th root or a 5th root or a 6th root. You could have any number there. It turns out that mathematicians decided, well, we're going to use the notation of fractional exponents to stand for square root symbols. So radicals can be written using fractional exponents. So when you have a square root, that's the same as a 1/2 power. Or if you have a cubed root, that's the same as a 1/3 power. The rule is the nth root of a to the m is either the nth root of a raised to the m power or a to the m over n. So you can use any of these. So let's put some yellow on here because this does need to be memorized so that you can go back and forth between radical symbols and fractional exponents. Well, because radical symbols can be written as fractional exponents, we're going to just have a quick review on fractional exponents. But I wanted to see what section you could review these exponent rules in. So let me just look at the table of contents and see. Oh, there's one called Exponents and Polynomials, Chapter 5. So the properties of exponents you can review in 5.1. So if you feel like these problems are just not registering well, then go to section 5.1 and review there. Hopefully you learned it in Math 094 well and remember it. We'll just look at it a little bit. In fact, I'm going to put yellow around these because you have to know how to use these. I'm not going to say name the multiplication property of exponents, but you have to have them memorized in order to use them. So let's put yellow around them. First, we have the basic definition of what does an exponent mean. So when mathematicians put that little superscript on the number right here, that means to take the base A is called the base, and multiply it times itself, n times. And when mathematicians put a 0 for our exponent, that's going to be defined to be 1. So a raised to the 0 power is 1 no matter what a is. Okay, so if you have 5 to the 0, it's 1. If you have 1.87 to the 0, it's 1. If you have negative 3 to the 0, it's 1. Why do I have to put parentheses around the negative? What if I have negative 3 to the 0 like that? Does anyone know what that is? Yeah. Good. Yep, negative 1. Because the 0, the exponent only applies to the 3 without parentheses. So be careful of that. Okay, the only thing that's not defined, 0 to the 0 power is undefined. You won't see that. Okay. And then we talked about this a little bit before. If you have a negative in your exponent, that doesn't make your answer negative. It just tells where in the fraction your factor should be. So if it starts out in the numerator with a negative exponent, you can put it in the denominator. If that factor is in the denominator with a negative exponent, you can put it in the numerator. So these are definitions. These are what mathematicians say this is going to mean, and so you can't really observe it. Properties, on the other hand, you can observe, because when you have a property, it's a result of the definition. So for example, here this property says if you have two bases the same multiplying together, you can add exponents. So that would say that here the m is the 3 and the n is the 2, and I could add exponents and get a 5. So that's 2 times 2 times 2 times 2 times 2. 2 times 2 times 2 times 2 times 2 is 32. But that's actually an observable property. It's just based on your definition. So here's your a cubed. That's 3 2's multiplying together. And here's your 2 squared. It's 2 2's multiplying together. So sure enough, you get 5 2's multiplying together. Same thing here. Multiplication is done by adding exponents. Division is done by subtracting exponents. So this property says I can just take the m, that's the exponent in the numerator, and subtract n, the exponent in the denominator, so I get negative 2. And then the definition says that's 1 over 2 to the positive 2, or 1 over 2 times 2. 1/4. So that is a property, so we should be able to observe why it's working. Why does that property work? So off to the side here, we can say 2 cubed is 2 times 2 times 2, and 2 to the 5th is 2 times 2 times 2 times 2 times 2. And so 3 of those 2's divide away, leaving the 2 times 2 in the denominator. So this is showing why. Why does that property work? So the subtraction divides away the common factors of 2. This rule says that you can multiply exponents. So here the 2 to the 3 to the second power, that's 6. This says multiply exponents that are outside the parentheses. 2 times 2 times 2, 6 times. And that would, in fact, be 64. And then this property 4 says that exponents outside the parentheses apply to each factor inside the parentheses. Notice this is just for multiplication. So that's A times B. I get a lot of students who take, in Math 104, they take 1 plus x squared and they say that's 1 squared plus x squared. Okay, that's not true. 1 plus x squared is 1 plus x times 1 plus x. And then you have to use FOIL and multiply that all out. It's actually a rule for division also. So we could write or division. But it's not for addition or subtraction. Do we have an example of that? I think we'll see an example eventually. Okay, well, let's go ahead and see how these how these exponents as fractions work, okay? So we're going to simplify numbers with exponents that are fractions. So here I have 27 to the negative 1/3. So looking at my rule, my definition actually, a negative exponent means I can put the factor in the denominator. So this is 1 over 27 to the 1/3 power, positive 1/3 power. And then the 27 to the 1/3 power, well, we saw up above that you can take that exponent and you can write it as a root. It's the cubed root of 27 to the 1 power. So I had asked you to memorize the cubes of 1 through 6 and the squares of 1 through, I don't know what I said, up to 15 would be really nice. Okay. If you didn't do that, though, you can still factor 27 and say, oh, that's 3 times 3 times 3. So the cubed root of 27 is 3. So the 1/3 power is the same as the cubed root, but the negative, put that in the denominator. So we have 1 over 27 to the 1/3 power, and that is 1/3. Anybody have any questions? Okay, well here's 125 to the 2/3 power. So we're using this rule right up here. Okay, so the 3, let's see, can I put both on this page at once? No. Okay. So the 3 is the n, and the 2 is the m. You can use this one, or you can use this one. In this problem, it's probably easier to use this one, the middle one, because then we'll have the cubed root of 125 like that squared, and that means you don't have to square the 125. Instead, you square the smaller number that you get from the cubed root. If you use the other expression, then you have to take 125 times 125 and then find the cubed root. But we're going to use this one, so again, that's one that hopefully you've memorized. But if not, you can factor it and say, oh, okay, 125 is 5 times 5 times 5, so the cubed root of that is 5. And then that cubed root is squared, so we have 25. So far we haven't used the definitions and properties we put in yellow. We just used the very top definition. I guess we put that in yellow too. The a to the m over n is the mth root of a to the m power. Well, I guess we did use this a little bit here. We'll try another one. Does anyone have questions? So the negative left of the 64 doesn't affect the exponent at all. You know, you're used to, oh, 2 negatives cancel. Well, they don't here, because the negative in the exponent here means put this on the other side of the fraction. So the negative in the exponent has nothing to do with the negative to the left. It just puts the 64 to the 2/3 in the denominator. So this negative to the left is just going to stay there, making your answer negative. Can you use this rule to rewrite that 64 to the 2/3 power? Like we did with the 125. So you need the cubed root of 64, and then that value gets squared. Did anybody memorize the cubed root of 64? Go ahead. So you get 4 squared. You can use the tree factoring with 64, but it's more involved because really you end up with 2's. So if you worked ahead and got 6 2's under the cubed root, you can do it that way. It's just more work. So you get the cubed root of 2 times cubed root of 2 6 times. So that's 2 times 2 or 4. Just in case somebody's wondering what that would look like. Okay, so you have, oops, yeah, 3 cubed roots of 2 and another 3 cubed roots of 2. So you get 2 times 2 or 4 right there. Well, on a calculator, you might want to be able to check this out. So if you look on your calculator, you might have an nth key on here, or you might have this little up arrow. Sometimes this little up arrow looks like y to the x, like that, instead of just having a plain up arrow button. So look on your calculator. You don't have to have this because you can always go back to this, but it is nice to be able to check your work. So if you think your calculator has either this or the up arrow button or the nth root button, then you can use your calculator to check things like 4th roots. So one way to type that in would be 81 raised to the parentheses 1/4 power, and you should get a 3. Another way would be to use this button, and if you have this button, you might put the 4 first, and you might put it second. It depends on your calculator. So you would try both of these, and then see, does either of these give me 3? So it's nice to know how your calculator works. And if you think your calculator does this, but you're not sure, you can see me after class, and we'll try and figure it out. Well, this brings us to square roots of negatives. The square roots of negatives are not real numbers. Because when we said the square root of 4 is 2, it was because 2 times 2 is 4. But we don't have any real numbers that multiply times themselves and give you a negative. So this will give us a whole new set of answers. And we'll define the square root of a -1 to be I. So we're going to make a new set of numbers to answer this question. Well, what is the square root of a negative? And we're not going to look at this today. We'll be looking at this in the future in a section toward the end of Chapter 7. So in 7.1, when you have the square root of a negative, just put that it's not real. I'm not sure how they phrase that. Let's see what they have. Yeah, you just put not real in all caps. And we'll introduce I more completely in a future section. And so this will be in a future section. All of this in a future section. So we'll talk about what to do with square roots and negatives in a future section. For now, in 7.1, you have these exponents, and so we'll be looking at some more problems with your exponent rules. So you look at your problem, and you look at your exponent rules, and you decide if any of them look like the same. So you have some multiplying going on. 2 of your rules have multiplying. You have multiplying in property 4, and you have multiplying in property 1. In property 1, the bases are the same, and that's what we have. We have both x's. So the property 1 rule says add the exponents, and that's what we do. So property 1 says to add the exponents, and this is why you need to have your rules memorized to use. it's easy to see when you have integer exponents how the rules work out, and that's why we looked at that example. But when you have fractional exponents, it's harder to visualize what's going on here. So off to the side, get a common denominator and add your fractions together. So the negative a half, I would get a common denominator of 4. So negative 2/4 plus 3/4, that's 1/4. These problems all say assume x represents a positive number because we're avoiding the problem that I said that we'll see in a future section. What do you do if your radicand is negatives? So we're avoiding that now. So multiply powers of x by adding exponents. How about this one? This one doesn't, it's got division, but the x and the y are not the same. On number 2, a is the same. So what we do is we actually use rule number 4 for division. And what I mean by that is the 3/5 applies to the numerator and the denominator. So you have y to negative 1/3 raised to the 3/5. You have x to the 4th raised to the 3/5. So rule number 4 for quotients, that the outside exponent applies to each of the inside, to each term in there. So it applies to the a and the b. Then we can use the rule number 3 that says multiply the exponents. Okay, so multiply the outside exponent times the inside exponent. Remember, multiplying fractions is nicer than adding. You don't have to save you don't have to have the same denominators, and you just multiply the tops together and multiply the bottoms together. So you can think of your 4 as a 4/1. So we get y to the negative 3/15, x to the 12/5. Negative 3/15 reduces. So we have y to the negative 1/5 over x to the 12/5. And again, it's not rule number 2 because the x and the y are not the same. They're not both x's or both y's. You can leave your answer like that, or if you want to write with positive exponents, you can move the y to the 1/5 into the denominator. You could have done that to begin with if you wanted to. There's not one way to use these rules. Does anyone have questions? So this negative 1/3 exponent, that applies to every single term in the numerator and denominator. It would be 64 to the negative 1/3, x to the 1/2 to the negative 1/3, 27 to the negative 1/3, and y to the negative 3 to the negative 1/3. So the outside exponent applies to every single factor, the numbers and the variables. So with the numbers, I'm going to switch them to other sides of the fraction so they have positive exponents. So 64 to the positive 1/3 and 27 to the positive 1/3. You can do that with the variables as well if you want, but some of these are going to multiply away, right? Because here I can multiply the exponents. So y to the negative 3 times negative 1/3. And x to the 1/2 times negative 1/3. So the outside exponents multiply times the inside exponents, and they apply to every single term, even those without exponents. So the 27 to the 1/3, well, that's just the cubed root of 27. And 64 to the 1/3, that's the cubed root of 64. And the exponent's 1/2 times negative 1/3. That would be negative 1/6. And negative 3 times negative 1/3 is 1. So the outside exponent applies to every single factor inside your product or quotient. And then it multiplies times exponents that are already there. And when there is no exponent, it becomes the exponent. If you have any questions on any of these steps, see me after class. Have a great weekend and a wonderful Easter.